What's up guys, this is Massey. Welcome to another video. In this video I want to talk about zero order reaction. What does that mean when we are talking about zero order reaction? It means that when we write the rate law, the rate is going to be equal to K times concentration of A to the power of 0. If you remember, the general formula for rate law is going to be rate equals to K times A to the power of N. If n equals to 1, we are dealing with first order reaction. If n equals to 2, we are dealing with second order reaction. And this case, when n equals to 0, we are dealing with zero order reaction. And as we saw earlier, K is the rate constant and it depends on the temperature mostly. And since A to the power of 0, we know any number to the power of 0 is going to be 1. So it's going to be K times 1. And any expression times 1 is going to be the same thing. So the rate of reaction for zero order reaction equals to just rate constant, which is K. So let's find out the integrated form of zero order reaction. So the consumption of A with respect to time, which we show it as negative delta A over delta T, has to be equals to K. And that's general for all different reactions when we are writing it for a reactant. We put this negative here because we need to have the rate as to be positive. So this part is negative times negative is going to be positive. Then for integration, we rearrange it like that. So negative delta A equals to K times delta T. Then what we can do, we can integrate it from A naught to A, which is going to be like that, and from 0 to T. It means that at time t, which is the initial condition, the concentration is going to be initial concentration, and at time t is going to be any kind of concentration during the reaction. When we rearrange it, we're going to end up having this expression, which is called integrated form of zero order reaction. That's the concentration at any time equals to negative K times T plus initial concentration. As you compare it with the linear function y equals to mx plus b. So when you graph the concentration of A with respect to time, if you are dealing with a linear condition, or it means that dealing with a straight line, it means that you are dealing with a zero order reaction. So I repeat it again. When you graph concentration of reactant with respect to time and you got the straight line, it means that you are dealing with a zero order reaction. So the slope is going to be negative K and the y-intercept is going to be the initial concentration. And it's going to be something like that. It's going down like that, and this one is initial concentration. So at any time you can figure out the value of the concentration. Depending on what kind of K value you got, you can get like this or like this. So for different K values, you're gonna get different slope. For larger values of K, you're gonna have steeper one. Alright, another concept is half-life of zero order reaction. Half-life means the time requires in order to have the concentration equals to half the initial one. So the final concentration equals to half of the initial concentration. And when we sub it to the general form, integrated form, instead of A, I put half the initial concentration. And then we solve it for time. In this case, time is going to be time half, which shows the half-life time. So K times time half equals to initial concentration divided by 2 when you solve it, and time half is going to be initial concentration divided by 2K. So that's going to be the formula for finding half-life of zero order reaction. Let's see some examples. First one, it says, let me take it out. It says the reaction A gives B plus C is known to be zero order in A and to have the rate constant of 5 times 10 to the power of negative 2 mole per liter per second. Before I start, I just want to show you the K, the unit for K has to be equal to unit for rate, because rate equals to K for zero order reaction. And since rate is mole per liter per second or mole per liter per minute, we're going to have the same unit for K as well. Sometimes it's shown like that: mole liter to the power of -1 second to the power of -1, or mole per liter to the power of -1 minute -1. Also, sometimes you might see mole divided by liter, they're shown by capital M, so it's going to be capital M divided by S, or M S to the power of -1. Sometimes you see these kind of different forms. So K is 5 times 10 to the power of -2 at 25 degrees. As I said earlier, with different temperatures, you're going to get different values for K. An experiment was run at 25 degrees where initial concentration is 1.0 times 10 to the power of -3 molar. Write the integrated rate law for this reaction. We got it earlier. A equals to -kT plus A naught. So that's going to be A equals to -5 times 10 to the power of -2 times T plus 1.0 times 10 to the power of -3. So that's going to be the integrated rate law for this reaction. Part B, it says calculate the half-life for this reaction. Half-life, we had the formula for zero order reaction. So T half equals to initial concentration of A with respect to divided by 2K. So initial concentration is given 1 times 10 to the power of -3 divided by 2. K is 5 times 10 to the power of -2. That's going to be 10 to the power of -3, 10 to the power of -1. It's going to be 10 to the power of -2, or 0.01 second. So it's going to be 0.01 second. It's going to be the half-life time. Alright. In part B, it says calculate the concentration of B after 5 times 10 to the power of -3 seconds, assuming initial concentration of B is 0. So that's going to be, we know the coefficient of A is 1, the coefficient of B is 1 as well. It means that negative delta A over delta T equals to delta B over delta T. So it means that delta B with respect to T is going to be equal to K, which is 5 times 10 to the power of -2. And delta T is, it says find it after 5 times 10 to the power of -3. So delta B, it means that change in concentration of B is going to be 5 times 10 to the power of -2 times 5 times 10 to the power of -3. That's going to be 2.5 times 10 to the power of -4. That's changing concentration. Since the initial concentration is 0, we're going to say the final concentration of B is going to be 2.5 times 10 to the power of -4 mole per liter, or molar. Let's see next example. Okay, this one, it says the decomposition of hydrogen iodide on finely divided gold at 150 degrees is zero order with respect to HI. The rate defined below is constant at 1.2 times 10 to the power of -4 mole per liter per second. So the rate, which is going to be the rate constant, 1.2 times 10 to the power of -4 mole per liter per second. That's the K value. If the initial HI concentration was 0.25 mole per liter, which is a 0.25, for simplicity I show it in A. So calculate the concentration after 25 minutes. So it says 25 minutes, but here you have it in terms of seconds, so it means that you need to change time to seconds. So 25 times 60 That's going to be 1500 seconds. After the start of the reaction. So we need to find out the final concentration. So A is going to be negative kT plus initial concentration. So we have A equals to negative 1.2 times 10 to the power of negative 4 times 1500 plus initial concentration, which is 0.25. That's going to be negative 0.18 plus 0.25. That's going to be 0.07 mole per liter. That's the final concentration of A. Part B, it says how long will it take for all of the 0.25 molar HI to decompose. It means that when the final concentration is 0, the part B, so it's gonna be A equals to negative kT plus initial concentration. So this one is 0, K is given, which is 1.2 times 10 to the power of negative 4. Time is the unknown, and the initial concentration is 0.25. So it's going to be 1.2 times 10 to the power of negative 4 times T equals to 0.25. T is going to be 0.25 divided by 1.2 times 10 to the power of negative 4. It's going to be 2083 seconds. Or if I divide it by 60, it's going to be 34.7 minutes. So this reaction is going to last for 34.7 minutes. After that, all reactant is consumed, so reaction is going to stop. Let's see the next example. It says the reaction is 50% complete in 30 minutes. How long after its start will the reaction be 75% complete if it's zero order? I'm gonna do this question in two different methods. Zero order reaction, negative kT plus initial concentration. That's the integrated form of zero order reaction. It says 50% complete, it means that still 50% of it is remaining. So final concentration is 50% of initial concentration. So that's gonna be A minus A naught equals to negative kT. So that's gonna be negative 0.5 A. It's gonna be negative kT. So the time is gonna be 0.5 A over K. The time is 30 minutes. So 30 minutes, 0.5 A over K. So K will be 0.5. Initial concentration is not given, divided by 30. So that's going to be the expression for K. Then it says, how long will it take to get 75% complete? It means that the final concentration equals to 0.25. Only 25% is remaining. So A minus A naught in this case is going to be negative 0.75. You know, negative KT. So you cancel the negatives. 0.5 A divided by 30 times T. Then A and A cancel out. T is going to be 0.75 times 30 divided by 0.5. So that's going to be 45 minutes. Let's see the next example. The initial concentration of the reactant is 0.75 molar. 0.75 molar, and it's reacting in a zero order reaction. The rate constant is 0.02 molar per minute. What will be the concentration of the reactant after 10 minutes? So after t equals 10 minutes. So we're going to say A equals to negative kT plus initial concentration. So it's going to be A negative 0.02 times 10 plus 0.75. So that's going to be 0.2 plus 0.75. That's going to be 0.55 molar. So that's going to be the concentration of A after 10 minutes. Part B. How long will it take the concentration to be reduced to 0.1? So again, we need to write the integrated form, but this time we have the final concentration. We need to find out the time. So this one is 0.1. K is given 0.02 times T plus the initial concentration is 0.75. So that's going to be negative 0.02 times T. 0.1 minus 0.75, that's going to be negative 0.65, negative 0.02 T. T is going to be 0.65, 0.02, that's going to be 0.65 divided by 0.02, it's going to be 32.5 minutes. So after 32.5 minutes, it's going to get into 0.1 molar. Let's see another example. Okay, in this example, it says the initial concentration of a reactant is 2 molar. So the initial concentration is 2 molar. It takes 30 seconds for the reaction to be reduced to 0.4 molar in zero order reaction. What is the value of rate constant, and calculate the half-life? So we can say A equals to negative kT plus A naught. That's what we had in for all zero order reaction. So this one is 0.4, negative K, 30 seconds, and here we have 2. So move with order, 0.4 minus 2, negative K times 30. That's going to be negative 1.6, negative K, 30. So K is 1.6 divided by 30. That's going to be 0.053 molar per second, or mole per liter per second. Both of them are the same. So that's the K value, part A. Part B, it says calculate the half-life. So T half equals to initial concentration of A, as we had before, divided by 2K. So initial concentration is 2, divided by 2, K is 0.053. 1 divided by 0.053 is going to be 18.87. What's the unit? The unit must be in terms of second. So after almost 19 seconds, it's gonna reduce to its half concentration. Let's see next example. The data table below shows the concentration of a reactant with respect to time for a zero order reaction. What is the value of the rate constant? So it's already said zero order reaction, and we know using the integrated form, we know K is gonna be A naught minus A divided by T. Because the slope is negative K, so just K is going to be initial concentration minus final concentration divided by time. So K will be equal to, initial concentration is 0.8, final concentration is 0.16, divided by 40 seconds is going to be 0.64 divided by 40. That's going to be 0.016. And the unit for K, here we have it in molar, mole per liter. This one is second, so it's going to be molar per second, or mole per liter per second. So that's the value and unit of K. I hope you enjoyed this video. Please leave me a comment if you have any question. Please don't forget to subscribe this channel. You can have access to many other videos regarding chemistry, physics, and math. Thank you for watching and have a great day.